Hi, I'm Malcolm, embedded software engineer here at SparkFun, and this is the new Qwiic capacitive soil moisture sensor. It contains a large copper pore in the PCB itself, which acts as a capacitive plate. We've marked the silkscreen of the board with a ruler on each side, so you know just how deep your sensor is inserted. The sensor also has an onboard blue status LED that you can light up to indicate if your soil moisture is too low or too high. In this portion, above the maximum depth line, is all the electronics. An important note here, the electronics are not waterproof, so don't stick them in your soil or get them wet while watering. Want to take your project to the next level by waterproofing the electronics? Look into conformal coatings that you can dip your board in, or design a 3D printed enclosure that snaps into the two mounting holes directly above the maximum depth line. And hey, if you come up with an awesome 3D printed enclosure for this thing, don't hesitate to share it. Post a Thingiverse link down in the comments below, or post a link to your project on one of our online forums so that you can share your awesome project with the open source community. Notice that for this simple, compact sensor, there are no headers or other connectors besides the two Qwiic connectors for I2C communication. This board has a software selectable I2C address, allowing you to connect several of these on the same bus and measure multiple planters or multiple soil areas in the same planter. This capacitive sensor offers one key advantage over resistive soil moisture sensors. It does not have metal leads which corrode over time. How do resistive and capacitive soil moisture sensors work? Let's get into it. Resistive soil moisture sensors are pretty intuitive to understand. They have two exposed metal leads that you insert directly into the soil. Then a voltage difference is applied across the leads. Since water and any mobile ions dissolved in it are more conductive than soil, it will have lower resistance, which, if you remember from Ohm's law, means that it will have a larger current between the two leads, which is what a resistive soil sensor is really measuring. However, the number of mobile ions is not exactly the same between water types. This adds an annoying feature to resistive soil moisture sensors. The same amount of different purities of water will yield different results. Also, as the DC current passes between the probes, the positive probe loses electrons and metal atoms that ionize and dissolve in the soil, physically eating away the metal, and the negative probe ends up with a crust of oxidation. Both of these can alter the readings of your sensor over time. The combination of the large variations based on water and soil type and the variation over time with corroded leads, resistive sensors can be a nightmare to calibrate. Luckily, there's a better way: capacitive soil moisture sensing. A capacitor is simply an energy storage device. A classic parallel plate capacitor consists of two metal plates, an insulating layer or dielectric between them, and wires on either side allowing current flow to the rest of the circuit. Now, let's apply a voltage difference across the two plates, like what would happen if they were connected to a battery. This will cause electrons to flow onto one plate, giving it a net negative charge. Similarly, electrons will flow off of the other plate, giving it a net positive charge. In this way, we can say that the capacitor is storing charge. Since opposites attract, these opposite charges pull on each other across the gap between the two plates. However, the dielectric layer between them is not very conductive and therefore stops them from jumping across. This tension creates an invisible electric field and is how the capacitor actually stores energy. The ability of the capacitor to store charge is called capacitance. For a parallel plate capacitor, the formula for capacitance is capacitance equals permittivity times area over distance. The area is simply the area of the plates and the distance is the distance between them. But what we will be most interested in is the permittivity. This permittivity is mostly determined by the dielectric constant of the material and largely is a measure of how well the dielectric polarizes. If the molecules that make up the dielectric naturally have a more positive or negative end, when the charge is stored on the plates and the electric field is induced between them, the molecules will align opposite the charge on the plates. They will then create their own electric field that opposes that of the plates. This decreases the voltage difference between the plates. The battery sees that there's more room for electrons and pushes more onto the plates so that the voltage between them is again equal to its own. Now, let's apply this concept to sense soil moisture. The copper pore in the PCB of our soil moisture sensor is sort of like an unfolded parallel plate capacitor. Instead of a battery, we connect this plate to the capacitive sensing pin of our CY8 CMBR3102 IC, which delivers rapid voltage pulses. Since we now have only one plate, the field lines from the ensuing electric field aren't simple straight lines like those of a parallel plate capacitor. Instead, the field lines loop from our plate through the soil. In this case, the soil is acting as the dielectric medium. Both soil and air have very low dielectric constants. However, H2O has a definite negative side and positive side. So if there is water in the soil, it is easily polarized. This has the same effect as a large dielectric constant material in our parallel plate capacitor, where it enables our capacitive plate to store more charge. This is then measured by the capacitive sensing IC. A little complicated, but it means no metal leads, no ever-changing readings, and no rapidly degrading sensors, making capacitive moisture sensors superior to resistive. Anyways, that was a whole lot of talking for something that just spits out a single number, which is capacitance in picofarads representing the soil moisture. I put together a little demo to showcase that number and how it could be used in your project. I have attached an OLED to my Qwiic capacitive soil moisture sensor to display a face for Mr. Moisture as we explore measurement of a completely dry cup of soil, a cup of soil that we've added a little bit of water to, and a fully watered cup of soil. We'll start with the completely watered cup of soil here. And as I insert all the way, you can see he gets happy. And you can also see the LED has turned off. The LED is currently indicating that our plant needs water. Now, let's shift him to this medium cup of soil. And you can see he's not really feeling it, but he's also doing okay. It's pretty meh. Switch into the dry soil and you can see he's at dead and the blue LED is on, so we need to water our plant. Thank you for sticking around and hearing about our new Qwiic capacitive soil moisture sensor. I hope that you find this sensor fun and that the physicists in the comments go easy on me for my clumsy description of capacitance. Anyways, be safe, have fun, and happy watering. In picofarads. Let's dive into project time. The shortest one ever, still messed up.